yesterday's group of problems, we got into a little bit of chapter 4. We started talking about polynomials, doing some different things with polynomials. Talked about naming polynomials. We're going to talk a little bit more about some chapter 4 stuff, and then we'll get into some chapter 5 stuff as well. Some other things to maybe kind of go over. Yesterday we talked about the quadratic formula and solving different quadratics and doing some different things there. I also would tell you that synthetic division, you're going to see some problems today with synthetic division. If I gave you a polynomial, let's say f of x equals, I'm just making this one up, it's not from the review or anything. And let's say that I divide it by x plus 3. A couple of things about setting this up and where people tend to make mistakes on something like this. First of all, we got to decide what goes in the box, right? And when I divide by x plus 3, what number will we put into our box? Negative 3. Yep. There's a couple of different ways that we had seen it. If it's written as a factor, like x plus 3, basically you would be saying, what would I get if I set that equal to 0? Sometimes they'll ask us to evaluate it, and it may say, let's evaluate that function at f of negative 3. That's the number I plug in. So if it's written as a factor, we do the opposite. If it's just written as a number and I want to check to see if that number is a 0, then we just put that actual number in. So a couple of different ways that we've seen that. Another thing that gets missed a lot here is we're going to put our coefficients, but notice that we're missing an x squared in here. So we got to put a 0 in where the x squared is. Also watch your signs, your positives and negatives. And then you should be ready to go through synthetic. So just wanted to talk more about setting synthetic division up, and then I think most of you guys do a pretty good job of doing synthetic and can do it from there. Remember that when we talk about the zeros of a polynomial, if I have a 0 of 4i, then negative 4i is also a 0. They always come in pairs. Same thing goes for a radical. If I said radical 7 is a 0, then negative radical 7 is a 0. They also come in pairs. If it's just a regular old integer like 6 does not come in pairs. Just because 6 is a 0 doesn't mean negative 6 is. But that's what we call the conjugates of each other. Works for i's and it works for radicals. You'll see a question about that today. And then you'll also see some where they're going to give you the zeros. You got to write the factors out. Like in this case, the factors would be x plus 4i and x minus 4i. We call these the factors of that polynomial. If I wanted to find the polynomial in standard form, I would have to do some FOIL here, and I would get my answer. Okay, vertical asymptotes. I always wrote VA. If you want to write out the word vertical asymptote, you can, but when you see that, you should remember that that means vertical asymptote. And in order to do that, we're always going to set the denominator equal to 0. If it's just a single factor like x plus 3, just set x plus 3 equals 0. If it's something that's like a quadratic equation that I may have to factor it. I may have to do like product and sum or something to it first. I may get a couple of factors, and then I would have to set both of them equal to 0. So you could have no vertical asymptote. If I just have like a number on bottom, that means there's no vertical asymptote. You could have one vertical asymptote. You could have maybe two vertical asymptotes if you had two factors on bottom. Okay, another question that you're going to see today is horizontal asymptotes as well. On horizontal asymptotes, this is based off of the degree. The degree is your highest exponent. We talked about that a little bit yesterday. And there are 3 rules to determine if there is a horizontal asymptote or what the horizontal asymptote is going to be. And so we're going to ask ourselves, is the degree on top bigger than the bottom? Is the degree on top less than the bottom? Or is the top equal to the bottom? And we're focused on the degree once again. If the degree on top is bigger, then there is no horizontal asymptote. Okay, it will not have one. If the degree on top is less than, the horizontal asymptote would be y equals 0, which is the x-axis. If the top is equal to the bottom, then we use the rule y equals a over b. And I'll give you an example here. Let's say we have 2 linear equations. These both have a degree of what, Majan?
2. It's 1. There's only one x.
1. Okay, this is just 1x. Okay, so they both have a degree of 1. Okay, that means the degree is the same. The top is equal to the bottom. Okay, and so then to write my equation out, your a and b values are your leading coefficients. So my equation here would be y equals 2 over 3. Okay. A lot of times there may not even be a coefficient here, so then it would be like 1 over 1. And that's the one we probably saw the most, if you had one like that. Okay, so you got to know those 3 rules. May not be a bad thing to add to your formula sheet. Okay, you got some graphing ones, some solving of inequalities. You can use the graph to determine that. Okay, then we are into chapter 5, starting with number 71, I think. Inverses is where we simply switch the x and y value. X and y are going to trade places. If it's an ordered pair, you just switch the ordered pairs around and you're done. Don't do anything with the negatives and the positives. Just switch the x and y. If it's an equation, x and y just trade places, and then typically you got to solve for y then. Get y by itself once you've switched it. We have exponential functions in chapter 5. Where we have something raised to a power of x. Because x is in the exponent, that's why we call it an exponential function. If a is bigger than 1, then it's a growth function. If a is between 0 and 1, then we call it a decay function. A growth function is going to grow as it moves from left to right. A decay function is going to decay or go down as it moves from left to right. And so when we talked about exponential expressions or exponential, we did some story problems with some of those where you had to show a situation. If I gave you a function like this is what we call, for this particular problem, we would say that this is my original function. And the reason I show you this is because a lot of people struggled with this in chapter 5 when we were doing this, especially the transformation part of this. And you're going to see a question or two today that has an example like this. So if I write out this expression, or this function, I want to talk about the changes or the transformations that are happening to get from the original to the new one. Notice the 3 doesn't change. Okay, so some people were trying to say what the 3 did to the function, and the 3 doesn't do anything. The 3 is part of my original function. The only 2 things that change it are the 2 and the 4. So the minus 2 right here is going to make this graph do what? Go right 2, okay. And then the plus 4 at the end, up 4. Okay. And the reason I kind of go through that is because I know that if it's just asking you for the graph, I know you can put that in the calculator and you can graph it. But if it's asking you to describe the changes, then you got to be able to identify what's going on. And sometimes it's hard to do that off of your graph, especially if you don't graph the original. Secondly, I think one of the things that's hard about a multiple choice test, some people love multiple choice tests because, we got 4 choices, you got 4 things, I know one of those is the right answer, right? But all of 4 choices are going to be very, very similar to each other. One of them might say right 2, down 4. One of them might say left 2, up 4, right? And so there's combinations there, and you got to decide which one is completely correct. And so some of them are close, they're just not quite there. And so I feel like that's what makes multiple choice kind of tough. So you got to really make sure you take your time. Don't rush through, especially on the wordy problems like that where you're describing what's happening. Okay, couple other ones here. And I'm probably going to go a little bit past 80 today, mainly because then tomorrow we can just go over anything that we need to cover to finish it up. There are 2 compound interest formulas that we talked about. Probably won't have both of them on the final, but you'll probably have one or the other. The first one is based off of time. And when I say time, I'm not talking about the number of years. I'm talking about, is it quarterly? Is it monthly? Semi-annually? Is how often I'm going to earn interest. Okay, so different accounts are going to make you interest different ways. This first one, the formula that we're going to use, is this, okay? And we just have to identify what's what. Remember, like, rate is your interest rate, N is the number of compounds, T is time. If you want to write some of those things down, if you don't remember what they are, then that's up to you. Make sure when you put it into your calculator that you put a decimal for your rate, especially. If it's 8%, you got to put in 0.08. The other one is compounded continuously. And the formula we use for that is P times E raised to the R times T. a lot of the same letters in there, a lot of the same variables. The only difference is that one uses the E number. Okay, some log rule things. One of the big things that we talked about with logs is a raised to the y is equal to x. That's the exponential form that we talked about. And then I could change this to log x base a equals y. Okay, so going from exponential form to log form, or vice versa, I think that would be a pretty big thing to put on your formula sheet. Having that on there is I think, a big part. There will be some where we just want to rewrite the expression, right? Change it from an exponential to a log or vice versa. You'll also use these two when we're solving an equation as well. So we use this pretty heavily in chapter 5 in lots of different ways. There's also what we call the change of base formula. If I have the log of 7 base 5, some of you, I know you have a calculator that has the log base button in your calculator, and you can type it in just like this. Some of you don't. So if you don't have that log base button, then you got to type it in like that. Log 7 divided by log 5. So it's really just a calculator problem, but kind of depends on your calculator. If I have the log of x, also remember that the base is assumed to be 10. These two things are the same thing. Okay, and so I'm just writing that up there so you remember that log is always base 10, unless there's another number there. If there's another number there, that's my base. But if there is no base, then it's assumed to be log 10. I could do the same thing for ln. If I have the ln of y, that's the same thing as ln base e of y. ln is always assumed to be base e. If there is no base, it's assumed to be an e. So log is base 10, ln is base e. Okay, the last thing for is I'm going to put 3 log properties up there. We talked, I think, about 5 of them, but 2 of them we don't hardly use much. So I'm going today to write 3 log properties up here. The first one is log of m raised to the n power. Remember that n can jump over the log. We use that a lot of times when solving equations. And then I could rewrite it as n times the log of n. Second one is our product property. You don't see a product here, but if there's nothing between the a and the b, we know that we are multiplying a times b together. It's kind of like if I write 2x. I don't always say 2 times x, but we know it's 2 times x. A lot of these problems are going to ask us to expand or write this as multiple logs. And so when I do that, we're going to say the log of a plus the log of b. And we're going to separate the a and b and put a log with each one. And we put a plus sign in between. And then the last one is called the quotient property, because we're dividing. Quotient means divide. So c divided by d. If I were to separate these two, this would be the log of c minus Those are your big three log properties. Sometimes we use it just to rewrite the expression. Sometimes we use it to solve an equation as well, where we got to get it down to a single log before we can solve it. All right, so that kind of gets you through 84 really, because it gets into some of the properties. I just wanted to get into the properties while we were talking about logs. So there won't be a whole lot to add tomorrow, but I'll add a few more things tomorrow. And then that